Alrighty, so for in this lab extension, you guys are going to be looking at different motions of carts and predicting what the graphs are going to look like, and then going and looking at what those graphs actually look like. So for the first one, we're going to have the cart start at the top of the hill. And we're going to say that that is starting at a position of 0. And then we're going to go ahead and let it go. And it's going to roll down the hill. And when it gets to the bottom, when it stops, or right before it stops because it hits it, we're going to stop that video. So what you're going to do first is you are going to make a prediction. So for each of these, this is where your prediction goes. In this column, you're going to make a prediction for your position versus time graph, velocity versus time graph, and your acceleration versus time graph. And then after you've made your prediction, we're going to go ahead and collect the data, and then you are going to record what you actually saw. So then we're going to record all 3 of those graphs. We're going to talk about the meaning of those graphs, and then we'll go from there and do number 2. So for this first one, I want you to go ahead and make those predictions right now. Go ahead and predict what the graphs are going to look like for both the position versus time, velocity versus time, and acceleration versus time graphs. Just know that I do expect you to make mistakes. So as you're doing this, it is actually a thing that if you make predictions, you are going to be more likely to learn from the activity and remember it, rather than me just showing it to you and you writing down the answers. So it is extraordinarily important that you go ahead and make those predictions, and just know that I expect them to be wrong. There's a reason why we have 2 sets of graphs here, one for your prediction and one for the actual. So please go ahead and predict. And as you're doing that, I'm going to point out a few things about this motion to keep in mind as you're making those graphs. So the first thing is it's starting at a position of 0. I know that because it's labeled on the graph itself. And the cart's going to be going down the hill. And I know anything that starts at the top of the hill and rolls down is going to be speeding up. And the other thing is that it's starting from rest. And I know that from reading the problem. So at the top, it's not moving. And as it goes down the incline, it's going to get faster and faster and faster. And so I need to be able to show that it's getting faster and faster. And the other thing to notice is that it's going in the positive direction. And I know that because the positive direction is here. So if I'm starting from 0 and going in the positive direction, then that means that I'm moving in a positive direction and speeding up because I'm going down the hill. So let's go ahead and take a look at what these graphs are going to look like. Alrighty, so we're going to go ahead and let this cart go at the top of the hill at that position of 0, and let it run down the hill. I'm going to go ahead and click collect. Excellent. And then right before it hit the end there, I went ahead and stopped it. So we can go ahead and zoom this in. And I want to look at a couple things here. I would like to look at, I didn't push the button right at the beginning. So the first part here is not going to match up exactly, but that's okay. All right, so this is what my data looks like. I was able to stop collecting data before it hit the bottom, so we're able to look at all of the data going that way. But one thing you'll notice is that I didn't let go of the cart right away at the beginning. So the beginning for time 0 is actually going to be here. So when you graph this on your paper for part F, you're just going to worry about what the shapes look like. So here for this first one, it's definitely opening up, a parabola opening upwards. So my position versus time graph is going to look something like this. My velocity versus time graph, you'll see, is a nice straight line going up at an angle starting at 0. So it'll look something like this. And then my acceleration versus time graph, if I go back to my graphical analysis and I'm going to click on here and I can tell it to look at the acceleration versus time graph. And what you'll notice is it actually looks really crazy. And the reason for that is that this is super zoomed in comparison to everything else. And each of the little data points fluctuate just a little bit. And so what I'm going to do is I'm going to notice that this is basically flat. And that is exactly what I expect. I expect this to be basically a flat line. All right, so when I look at my acceleration versus time graph, you can still see here at the beginning that I really hadn't done anything yet. And every time you do it, you go from a position versus time to velocity, and then from velocity to acceleration. There's going to be a little bit of a delay before the data actually looks right. And the reason for that is because to look at velocity, you need to look at two different positions. And look at how far it went and how much time that took to calculate your velocity. And then for acceleration, you have to pick two different velocities and two different times to then be able to figure out your acceleration. And so in order to have those two different positions and then have those two different velocities, it's going to take a little bit of a time. And between here and here is only, between here and there is only half a second. So it makes sense that you're going to have a little bit of weirdness for a fraction of a second, so that way it'll kind of even out. And then this part looks really bumpy, but in reality, the difference between here and there is 0.05 meters per second squared, which is basically nothing. So we're going to consider this to be basically a straight line. So in terms of our three graphs, then we will have a straight line. And I know the acceleration is positive because this was my horizontal axis here. Here's my horizontal axis, that's t. And the line was above it at a positive number. So it's up here at 0.175-ish. So I know that we're good there. All right, so the next thing that we're going to do is we're going to take a look at number 2. All right, so how did you know to get these graphs? The first thing is that we know it started from rest, and we know that the velocity on one of these graphs is equal to the slope on a position versus time graph. So right here, my slope is 0, which means that my velocity is 0. And I also know that my position is 0 because my y-intercept is 0. And then at the end, I know that I have a positive position because the height of this is positive, and that means that my position is a positive position. But in terms of my velocities or my slopes, I know that this is a positive slope because it's going uphill. All right, so if we have a positive slope, that means that we have a positive velocity. And for this unit, we're going to have uniform acceleration, meaning that it'll be a nice curve as it speeds up. On our velocity versus time graph, we know that our velocity started at 0 because our y-intercept is 0. And at the end, we know that it's moving forwards because it's high up. Now, if you wanted to go from your position versus time graph to your velocity versus time graph, all you have to do is look at those slopes, because the slope on a position versus time graph gives you velocity, and the slope on your velocity versus time graph is going to give you the next one. And we just have to talk about what that means. So here at the beginning, your slope is 0, which means that that's how you know your velocity is 0. And up here, your slope is positive, which is why you're going to end up with a positive velocity at the end. Now, just like when we're finding the slope on a position versus time graph, the slope is going to be the rise, which is your change in position, divided by your change in time, because that's the run. That's how far it goes sideways in the same amount of time. And so that is the definition of velocity. It's how much your position is changing in a certain amount of time, which would describe how fast you went. How far did you go and how long did that take you? Okay, then I know how fast you're going. So your slope on a position versus time graph is your velocity. So by the same token, if I look at my velocity versus time graph and I think about what the slope means, the slope is again rise over run. And our rise is going to be how much it goes up, which is my change in velocity, because that's this way. And then divided by my run, which is going to be the other way. And if you think about how much it goes up, my rise for this velocity versus time graph is 0.5. If I go from here all the way, let's say we go to right there. And so my rise is 0.5. All right, then I'm going to go ahead and divide by how much time it took to go from one place to the other. And I can't just use 3.75 because I am not starting at 0 here. This is more like, oh, I don't know, let's call it 0.85. So to know how much time actually happened, I'm going to need to subtract these two from each other. So my change in time then is going to be the 3.75 minus 0.85, and I'm going to get 2.9. All right, so I'm going to go ahead and take this, my change in time, I'm going to plug it in here. So I get 0.5 divided by 2.9 seconds. And when I do this, I'm going to have meters per second divided by seconds. And that is going to cause it to be meters per second squared. And when I do 0.5 divided by 2.9, I get 0.172. So if I come down here and I look at my other graph, yep, that looks about right. It is crossing the graph at about 0.172. So that's perfect.